I'm glad to be here and see so many people here for this tutorial. I want to point out that's indeed a tutorial. I was asked to talk about SNOM, and that there will be people in the room that eventually have not heard about it. So for the experts in the room, and I guess there will be some of them, if you get bored, feel free to leave. But I do my best to show for everybody a little bit. So I want to talk about basically the instrumentation of s-SNOM, which is scattering type scanning near-field optical microscopy. And the idea of this technique is to beat the diffraction limit to perform optical imaging on a nanometer scale independent of the wavelengths. And the basic principle is shown here. Here a more schematic drawing, here a little bit more fancy drawing, but both are the same. So essentially, what we use is an atomic force microscope, and I assume that you all know what that is, with which we get a topography surface. And to make that microscopy seeing kind of colors or what is below the tip apex, we shine light onto the tip and collect the backscattered light. I will go into detail. And by recording the tip scattered field as a function of the tip position, we obtain nanoscale resolved images. There are a couple of things to solve. For example, here you can see this in a bit more details. So we use a focused laser beam. This focused laser beam has a diffraction limited spot size, and so we get a lot of background scattering. That's one problem that we solve with the NeoSpec technology. But then we have this tiny little nanofocus here, and this nanofocus interacts locally with the sample surface, and is the reason why we get this nanoscale resolved imaging. And to give you a brief example, that's a sample that was designed as it is shown here. That would be a far-field image, and this is the images that we get by recording the tip scattered field as a function of tip position. So I want to say this technique goes back to the developments in the 90s by Kawata, Vikramasinghe, and so on, and then was brought actually to the infrared, essentially by Fritz Kallmann, and I joined him then around 2000. And so all I show you here is how we brought this technology then to, let's say, a commercial product that reliably gives these nanoscale images. So here's an outline. It's not exactly how the NeoSpec is constructed, so it's a bit more general view. So you see here the atomic force microscope tips that we use here in a schematic view. That's the tip, the cantilever, and we operate the AFM in tapping mode. That means we oscillate the tip at a frequency omega. That's important to keep in mind. And then we can use monochromatic laser sources. We use a parabolic mirror. We focus the light onto the very tip apex, and then we collect the backscattered light. Now, an important aspect is that we don't detect the intensity of the backscattered light, but we use here a Michelson interferometer to collect amplitude and phase. That is important to get both complex valued information about dielectric properties, but it's also important to suppress background scattering. On top of that, we do not collect the light that is scattered by the tip, but the light that is modulated through the tip oscillation, and then we do not demodulate the signal at the modulation frequency here, but a higher harmonic of it. That's crucial. This higher harmonic demodulation, how we call it, plus the interferometric detection are key for getting nanoscale resolved images that are background free. And I will guide you through how this works and why it works. So that's a Michelson interferometer, as I said, and we use monochromatic lasers. Now, with the same setup, we can also perform spectroscopy. So in this setup here, we get images. But if we are interested in getting a spectrum with nanoscale resolution, then we can use the same setup, but instead of a monochromatic laser, we use a broadband laser source. It could be also a synchrotron. Some people use synchrotrons. But essentially, an infrared supercontinuum is used for that imaging. Now, in this case, this Michelson interferometer is used as a so-called asymmetric Fourier transform spectrometer. So at a fixed tip position, what we do is we move this reference mirror of the Michelson interferometer, and that way we get interferograms. And this is the same principle as we have in a standard Fourier transform infrared spectrometer, with one tiny little difference, namely that the tip and the sample here in one of the interferometer arms. And this is different to a standard FTR spectrometer. And it's important because it allows us to get amplitude and phase spectra when we Fourier transform this interferogram. So this is what we measure at the detector. That's what the NeoSpec is doing. You can even get this spectra, these interferograms out, but typically you may look at directly at the amplitude and phase spectra that are obtained by Fourier transform of this interferogram. As I said, because of this asymmetric design, you get an amplitude and a phase. And we will see later on that an amplitude spectrum corresponds to something that would correspond to a reflection spectrum, while a phase spectrum sounds a little bit weird, but the phase spectrum actually gives you an absorption spectrum. So that means we can measure, by light scattering from an AFM tip, we can obtain something that corresponds to a reflection and to an absorption just by this interferometric design. Okay, so now what's the basic probing mechanism? So here I show you a numerical simulation where we have a tip illuminated with, in this case, a terahertz beam with a polarization that points in this direction. It's p polarization. And what happens is that this incident field polarizes the tip, indicated here by the minus and plus charges. Of course, this charge oscillation, this charge distribution is oscillating at, in this case, terahertz. And this is schematically shown here. So the incident field induces a dipole in the tip, and the charge accumulation at the very tip apex gives rise to a very strong electromagnetic field, which we call here a nanofocus or hotspot. And this is a near field. It's concentrated around the tip apex. It's not propagating. It's just there. And it's highly concentrated and carries very high momenta. As long as the tip is far away from the from anything, from a surface, this near field is just there. But it's doing nothing. So the light comes in, it polarizes the tip, and then scattering occurs. But now, if we bring a sample closer, then what happens is that this near field at some point will touch the surface of the sample surface, and these near fields, these highly concentrated fields, they undergo reflection analog to what happens with a far-field beam. So these near fields are reflected, and they act back on the tip and lead to an additional polarization in the tip apex, which I indicate here by a blue arrow here. And this additional induced dipole moment leads to radiation, and that is indicated here by the blue arrow. Now I want to point out that the different color does not mean here that we have a different frequency. What we see here is elastic light scattering, but I use blue color to indicate that this is scattering due to what we call a near-field interaction between the tip and the sample, okay? Now, if we come closer, more near-field get reflected. This induced dipole in the tip due to near-field interaction between tip and sample intensifies, and we get more scattering out here. So that's why I draw this arrow here more intense. Now, we are interested actually in the light that comes from the near-field interaction and not from the scattering of the background of the tip. So we have to somehow extract this light here, and I will show you in the following how we are doing this. So here, that's a summary of what I showed. If you bring a tip closer to a sample surface, we get near-field interaction between tip and sample. Near-field here intensifies through reflection of the near-field at the sample surface. That gives rise to additional scattering from the tip. And this additional scattering depends on the dielectric properties below the tip apex here. The dielectric properties in the following are described by the dielectric function or the permittivity of the sample surface, epsilon. Okay, so as I said, we are interested in the light scattering that arises through this near-field interaction. But we have all this light coming from this huge dipole here, and this is what we call background scattering, and it's really huge. So we need a trick to extract this light here, and we do it by what we call higher harmonic signal demodulation, and I try to illustrate this a little bit here. Now we have two contributions, as I said. We have a near-field contribution, this black arrow, and background contribution. And if you approach the tip towards the sample surface, this near-field interaction, or scattering due to a near-field interaction, it occurs only if the tip is very close, much closer than the tip radius here, right? However, the scattering that arises through far-field illumination of the tip occurs on a much larger scale here, and it is due to the reflection of the incident beam here at the sample surface, which gives rise to a standing wave pattern above the surface. So the tip is actually illuminated here by the standing wave pattern here. And if we move the tip up and down, then we see these oscillations here. But these oscillations are on a scale of the wavelengths of light, right? While this one is on the scale of the tip radius. Now, if we oscillate the tip through using tapping mode, the tip is oscillating at a frequency omega, then the tip samples this field here. Here we have a very strong nonlinear behavior with distance, while here it's more or less linear. So now if we assume that the tip is oscillating sinusoidally, that would be now here the time axis, and here that's the tip sample distance, here sinusoidal motion. Now, what this gives rise to is an anharmonic signal in time, because the tip oscillating in this direction moves through this nonlinear field distribution here. So that means we get here an anharmonic signal. While the background is more or less linear, so if you look back here, also this is sinusoidal, but if we modulate here on a scale of 10 to 20 nanometer, which is much smaller than the tip radius, right? Then this behaves more or less linear, and if the tip is sampling such a linear signal, we get a harmonic signal in time. So that's a very important aspect. Here we get an anharmonic time dependence, and here a harmonic time dependence. And what we do now is simply making a Fourier transform of this signal here. So the s-SNOM is doing that automatically. And now we have the two contributions. The near-field contribution gives rise to higher harmonics because of the nonlinearity, while the background contribution occurs only at first or second harmonic, but not at higher harmonics, because that's a harmonic signal here. And this is what allows us to separate or to extract the near-field signal. We simply measure at 3 or 4 times the modulation frequency, the tapping frequency that we use to operate the AFM, because of this linear behavior of the background. That's, of course, all very, let's say, very, very rough, but it works very nicely. So I would say, from practical point of view, the third to fourth harmonic, signal harmonic, is typically background-free. Another thing I want to mention, I don't go into detail, that only works because of the interferometric detection. That's an important aspect. I don't have time to go into that. Please keep that in mind. If you would measure that without interferometric detection, it would not work that nicely. So that's an example here. That's in the visible. Here we have this oscillating tip, and what we are doing now is a so-called approach curve. So the tip is oscillating, and then we move it towards the tip or backward. And what we see here is the tip above a gold surface. We use a 600 nanometer wavelengths. We retract the tip, and we look at the signal demodulated at the modulation frequency. And what we see is that the signal, once you retract the tip, or the oscillating tip, right, it decays, and then we have these oscillations as I draw schematically before. This here, marked in red, is the background signal, while this is the near field. But you see already it's hard to distinguish background and near field. If we then just turn or go to the second harmonic or to the third harmonic, what we see is that these background signal oscillations, they become smaller and smaller, the higher the harmonic, and only the near field remains. So if we bring the oscillating tip very close to the sample surface, we see this huge increase in the signal, which is now completely background-free. But what you also notice is that the signal to noise becomes worse. So that's the drawback of this technique. The higher the harmonic, the noisier the signal becomes. But nevertheless, we have to live with that, and it works actually quite nice if you operate typically with the third to the fourth harmonic of the oscillation frequency. That's an example. That is an AFM image of a triangular gold nano islands. You see them bright here because they stick out about 20 nanometer height. That would be an image recorded at the first harmonic. You see everything is blurry. The gold particles occur dark. Also, their refractive index is higher than that of the silicon. But now, if we switch to the third harmonic, we see a very clean image, free of these background interference oscillations, and we see that the gold islands are bright on dark background, because gold has a higher reflectivity as the silicon, which is actually true in the near field as well as in the far field. So I want to say that this background suppression works better and better the longer the wavelength is, because these oscillations of what is standing wave pattern, the scale on which this occurs scales with the wavelengths. So if we oscillate the tip at 20 nanometer, then if we go to infrared, these oscillations, they are on a scale of micrometer. And so here we can see this very nicely. These are approach curves at 500 nanometer wavelengths and here at 6 micrometer wavelengths. So there's a factor of 10 difference. And we see that while here we have these very pronounced oscillations, they are much less pronounced in the mid-infrared. Nevertheless, we see that there's still a little bit background left at the second harmonic, but if you go to a third, fourth harmonic, we see that in the infrared as well as in the visible, we can nicely suppress all this background here. So that's a zoom out, and you see that in the infrared, these oscillations from the background occur as well, but here they are on a much larger scale than in the visible spectral range. So I want to talk now a little bit about near-field contrasts. So why do we, or what is the origin of contrasts that we see in a SNOM? Why is it possible to distinguish materials? And I want to, there are various different models and also numerical simulations, but I want to talk here about a very basic, very simple model that was actually the first one that was developed, actually by Fritz Kallmann and Bernhard Knoll, his first PhD student here when he was in Martinsried. And it's based on the idea that we replace the tip here, that's a tip, a numerical simulation showing the field distribution at the very tip apex. In the model, we replace by a small sphere. The reason is that the field distribution at the very tip apex looks very similar to that of a small sphere. But a small sphere can be very nicely modeled by a point dipole that sits in the center of the sphere here. Okay, that's the basic idea. Now, we bring this dipole above a sample surface, we illuminate it, and then we calculate, and we can calculate it actually analytically, what is the scattering from the dipole in such a virtual sphere sitting here in the tip apex of the tip. And that's how it goes. I go very quickly through that. So the scattered field here is proportional to this dipole that sits here. And I show already the next slide here. So this dipole actually sits above the surface, and for that reason, the near fields are reflected. But the reflection of near fields is analog to the dipole kind of interacting with its mirror dipole. That's a concept that we borrow from electrostatics, the mirror charge method. And here, we just, instead of mirror charges, we have here mirror dipoles. So this dipole P interacts with its mirror dipole P prime. And P prime is here depending on this factor, which is called the near-field reflection factor, or the surface response function, which is epsilon minus 1 divided by epsilon plus 1, where epsilon is the complex valued dielectric function of the sample surface. Now, this mirror dipole interaction gives rise to an effective dipole that we describe here by PF. That's the effective dipole moment, and it's here. So the light that is scattered by this dipole here is proportional to the effective dipole moment, P prime. Now we have to consider also that this tip is illuminated by the incident field, and then we have scattering in this direction, but we also have far-field reflection of the incident field at the sample surface here, which is described by the far-field reflection coefficient R. And that's why we have here this additional term here, which is 1 plus r to the power of square. The square comes from the fact that we have the incident beam being reflected and the scattered beam being scattered directly, but also via reflection here. That's why we have this here. So the near field actually, or the field scattered from the tip, is a mixture of scattering from a dipole in near field interaction with its mirror dipole and this far-field reflection coefficient. And for that reason, the far-field reflection coefficient and this near-field interaction are somehow a little bit mixed up, which is sometimes important to consider if one wants to make quantitative analysis of near-field images and spectra. Now, after solving this problem here analytically, which is actually not very difficult, but I don't execute it here, we find that this effective dipole moment here can be described via an effective polarizability, which is given by this rather simple equation. So the effective polarizability of this dipole here is the polarizability of this virtual sphere that we have here, divided by this term here, in which we have a factor beta, which is this one here, the near-field reflection coefficient, that is exclusively a function of the dielectric function of the sample here, and the distance z and the tip radius. Now, if we assume that we keep the tip radius here constant and the distance as well, so z and a are constant numbers, then this effective polarizability only changes if beta changes. That means if we move the tip from one material to the other. Okay? So that's a very simple model. And in case that this beta is small, that means if dielectric function is dielectric and weak, then this reflection factor beta is smaller than 1. And in this case, the effective polarizability of the tip to which the scattered field is proportional is roughly proportional to the near field reflection factor. So that's what we learn here. So for example, this is valid for polymers, proteins, and so on. Also not for metals and crystals, but for these what we call weak oscillators, this is valid. So the effective polarizability, which is a complex valued number, is proportional to the complex valued reflection factor in the near field. So that's more or less what we see here. Now, how can we use now this model? I just want to briefly outline this. So that model is developed here or shown here for the tip dipole being at a fixed distance here. But we can also simulate very easily this high harmonic demodulation by simply assuming that the tip is oscillating. So what we do is we calculate the effective polarizability as a function of time. And we assume that the distance, z, is oscillating sinusoidally as a function of time. And then we can take this tip motion, a sinusoidal tip motion, we plug it into this effective polarizability. And we get here this time course, like in the experiment. We do a Fourier transform, and we can calculate here these enharmonics. So this is what typically is done. And we can then compare experimental values with these calculated values. Now, I want to say that this model, this simple point dipole model, it gives a very intuitive and good picture, but qualitatively, in many cases, it's not very good. And for that reason, a variety of other models were developed that are a bit more realistic, because obviously the tip is elongated, and for that reason, a point dipole is not. It's a rough approximation, but it's not really realistic. For that reason, many years ago, one of my PhD students developed what we call the finite dipole model, in which the tip is modulated by a finite dipole described by an ellipsoid. And without going into details here, I refer just to this paper here. We can find an equal expression or an analog expression for the effective polarizability of this finite dipole, and we find again that it depends on this reflection factor beta here, right, which is the near field reflection factor here. So that was all a little bit theoretical, so I want to give you a couple of ideas what we can do with that, or what we can learn with that in terms of spectroscopy. And so here I made an artificial material that is comprised of various different material excitations here. Namely, as I said, this is a bit of an unrealistic material, but let's assume we have here a material that has some electrons, and for that reason, we can describe the response by a Drude term. Then we have, let's say, some phonons in there that would give then, or could be described by a strong Lorentz oscillator. And let's say at lower frequencies, we have some molecular aberrations on excitons, and that could be described by a weak Lorentz oscillator. So if we have these three contributions and we sum them up, then we get this, as I said, a bit artificial dielectric function, where I plot the real part of the permittivity and the imaginary part of the permittivity, and we get these typical behaviors. So let's start here. That would be the dielectric function for a weak oscillator. We see here this dispersive like line shape of the real part of the permittivity that is accompanied by this bell-shaped imaginary part here. So that's like nothing fancy, just a dielectric function that would describe a molecular vibration and exciton. If the oscillator becomes very strong, we have a similar behavior, but now the permittivity can assume even negative values. And if we go to lower frequencies where the Drude term becomes active, then we see that below the plasma frequency, we have negative permittivity all the way down to DC values, while the imaginary part strongly increases. So this is a dielectric function, and that we can now plug into our dipole model that I showed you before. We assume now that the tip is oscillating and that we demodulate the signal, and then we can calculate what we would measure if we measure interferometrically amplitude and phase signals. So, and here we can see how a dielectric function of a sample translates into an s-SNOM spectrum or a nano-FTR spectrum. And what we see here is actually that it looks quite similar. For the Lorentz oscillator, the weak one, we see that the amplitude spectrum actually looks pretty much the same as the real part of the permittivity, while the phase, and this is very important, the phase follows more or less here the imaginary part. So if we measure the phase, then we understand now why the phase kind of gives us the imaginary part. That means the absorption of the material. And that is possible due to interferometric detection, that we measure the phase. And so by doing a scattering experiment, we have access to the absorption. And the real part of the permittivity, well, is kind of corresponds to the far-field reflectivity, and that's why if we measure an amplitude signal, we measure the reflection properties of the sample, just on a very small scale. If we go now to strong oscillators or to plasmons, then the situation becomes a little bit more tricky. We see now that here we see that the peak positions are more or less the same between the dielectric function and the SNOM spectra. If we go to these strong oscillators, we see that there's a strong peak shift. We don't probe anymore the real part of the dielectric function, but we see a response that is shifted to higher frequencies. And the reason for that is actually that if we look now at this beta, at this near-field reflection factor, we see that dielectric values now become negative, and if we plug them in here, then we see that this denominator here becomes very small. And we find that, we see that epsilon here passes through 0. That means this denominator can become very large. And that means that the near-field reflection factor can be larger than 1. That's an interesting phenomena, actually. We all know that a far-field reflection cannot be more than 100%. Near fields, however, can be reflected by more than 100%. Namely 200 or 300% even. And the reason for that is that the near fields that are created at the tip apex here can excite so-called surface polariton modes. These are resonant surface excitations that cannot be excited by far field, and they can boost the reflection factor to beyond 100%. No worries, that does not violate any energy conservation, simply because we are here in the near field. There's no energy propagating out. These near fields are staying where they are, but they can introduce these enormous high polarizations that give them rise to this peak here. And this peak is shifted because it's a different excitation to what we see in far field. So these are excitations that we cannot see directly in a far field spectrum, and they occur at different spectral positions. That is important to keep in mind. And the same happens actually if we go to metals, where we see here a peak occurring close to the plasma frequency, and what we excite here is a surface plasmon polariton, while here we have a surface phonon polariton. So to summarize that, if we look at metals close to a plasma frequency or to crystal strong near their rest Strahlenband, then we observe a surface plasmon or surface phonon polaritons in the near-field response. And they have not really an analog in far-field spectroscopy. And for that reason, if you have such excitations, you really need to do modeling to interpret our near-field spectra. That's very important to keep into mind. While if we look at molecules or PMMA or these weak oscillators, then we can just take this near-field spectrum and compare it with a far-field spectra, and we see that they match quite nicely, and we can avoid complicated modeling. Okay, so now I have a bit more complicated slide here. So, but I want to. I think I skipped this here because I think I'm running already a little bit out of time, and I have a couple of more slides. So what I described so far is was for bulk material. Now I think most of the people are interested in 2D materials, and one can use this dipole model here to also describe thin layers or multi-layer samples. And in this case, what we are doing here is, well, I need to go back to this slide here. So if you have a multi-layer sample, then what we have to do is we describe the response here by the Fresnel reflection coefficient here. And this Fresnel reflection coefficient cannot be calculated for far fields, but it also can be executed for near fields. And in this case, things become a little bit more complicated. So that's the dipole model that I showed you before. So I go back briefly to if we have this expression here. So remember, we have the effective polarizability here, where we have the polarizability of the tip, and then we have this term here, which is expressed by the near-field reflection factor. Now, in a more general model, this polarizability is described by the polarizability of the tip divided by 1 minus polarizability of the tip, and then we have here the Green's function. And this Green's function now is given by this, let's say, rather complicated integral. And this integral contains the reflection coefficient of the sample, this multi-layer reflection coefficient, as a function of the in-plane momentum. And then we have here some terms. That's the so-called coupling weight function. That's just a kind of an angular spectrum representation of the near fields below the tip apex here. And it has this form here. So that's the momentum. And here we have this coupling weight function. And we find that it has a maximum exactly where the momentum is around 1 over the tip radius. So in simple words, what that means is that the polarizability here, the effective polarizability of the tip here, is kind of an integral over the reflection coefficient of the sample weighted with this function here. And this weight function has a maximum over 1 over r. That means with s-SNOM, we probe the reflection coefficient around in-plane momenta that are determined here by 1 over r, where r is the tip radius here. So that's the important point. Now I want to give you some examples here. So that is some work from Dimitri Basov's group. And what they did here is they looked at thin TMDs. So I think this was a tungsten deselenide, and they looked at monolayers, 3-layer systems, and so on. And this material is known to have an exciton, and the exciton can be described by a weak oscillator. If you remember, that was on the right side in the spectrum that I shown before. And so they performed a series of images here, amplitude, and these are phase images, and they scanned this at various different frequencies. And from these monochromatic images, they can construct a spectrum. Here we have an amplitude spectrum as a function of frequency, and here the phase spectrum as a function of frequency. The data points are extracted from these images, and we see here this typical dispersive behavior in the amplitude spectrum, and this bell-shaped spectrum in the phase. And now what they did is they used a dipole model, exactly the one that I showed, using the multi-layer reflection coefficient, and they tried to fit now the experimental data by using a dielectric function. And the dielectric function that they found that optimally matches here, these data points, is actually the one that you see here. And as far as I understood, I think this was the first time that from a monolayer on a nanometer scale, the dielectric function related to this excitonic excitation could measure on a very small scale. Because this, of course, is hard to measure by standard far-field spectroscopy, measuring amplitude and phase. One could do eventually with ellipsometry. But of course, on such small flakes, this is difficult to do. So that's one 2D materials application, measuring the dielectric function of small flakes, and here related to the exciton. Another example that I want to briefly show, another prominent example, that's from Thomas Taubner, who sits actually here and is happy that I show this. Here they looked at single layer and bilayer graphene. And from far-field spectroscopy, that's a far-field spectrum, is shown that there's an interband transition around 400 millielectron volts. But this exists only in bilayer graphene, but not in monolayer graphene. And so what they did here, they used a tunable laser, tunable in this spectral range here from 200 to 500 millielectron volts. And you can see already that the contrast between bilayer and single layer graphene is nicely visible, and that it changes as a function of frequency. So now one can do the same game. One can take a bunch of images and reconstruct a spectrum in amplitude and phase. And so what they could see here is this typical dispersive light behavior in the amplitude and the bell-shaped behavior in the phase spectrum here. So one can nicely understand this. One could, from that, eventually get the dielectric function that is related to this interband transition. And importantly, this is really seen only in bilayer graphene, and on the single layer graphene, the spectral response is completely flat here. All right, so then how much time do I have left? 5 minutes. OK, so then I just want to briefly mention another important application. We will, I guess, hear a lot about that in the next days, which is polariton imaging. So in 2D materials, we can have a variety of electromagnetic modes that exist when the 2D material has a permittivity that is smaller than 0. In this case, these materials can support electromagnetic waves known as polaritons. And they can exist in a variety of different materials based on different excitations. For example, in graphene, when graphene is doped, the permittivity is negative. And in this case, electromagnetic waves can propagate in form of surface plasmon polaritons. In hexagonal boron nitride, in form of phonon polaritons. Here the negative dielectric function arises due to the existence of optical phonons. In TMDCs, one can have excitons that are very strong, and then the permittivity can become negative. You have exciton polaritons, and so on. So the interesting thing about these polaritons is these are waves that propagate along the sheet here, and their wavelength is extremely compressed to the photon wavelengths, and their field extends in vertical direction only a fraction of the photon wavelengths. And this is shown here for graphene plasmons. So this is a numerical simulation that shows the electric field of a graphene plasmon. So we see here these field oscillations. That is one wavelength. And we see that the field extends in vertical direction only a fraction of the wavelengths. Just for comparison, that's the corresponding photon wavelength. So that is half the wavelength of a photon. Once we manage to convert that into a plasmon, polariton that propagates along the graphene sheet, then we obtain this. So we can get an enormous compression of of electromagnetic energy into these surface waves here. So why is this related with? I need to go a bit faster, otherwise don't make. So how is this related to SNOM? Well, as I said, these waves have extremely high momentum, much higher than the photon momentum. That means by reflection or transmission of a far-field beam, we cannot excite these modes. However, if we have now our s-SNOM, and we bring it close, in this case a graphene sheet, and we shine light onto the tip, then these near fields, they carry enough momentum to launch these polaritons in the graphene sheet here. What happens is that the tip launches them, they propagate away, eventually not being visible. However, if we scan close to an edge here, these waves are back reflected, and they hit the tip and then polarize the tip again. If we now collect the backscattered light and we scan near an edge, the images that we observe are these ones here. And we see now, instead of a homogeneous, let's say, response between graphene and silicon carbide here, which is the support for the graphene. Remember the image that I showed before on the bilayer and bilayer single layer and bilayer graphene, they were homogeneous. But now the graphene is inhomogeneous. We see these fringes here. And these fringes are nothing else than the manifestation of graphene plasma polaritons that propagate from the tip towards the tip and then back. Whenever we have here a maximum, we have a constructive interference on this path here. And whenever we have here a minimum, we have a destructive interference. So in principle, this is a kind of a plasmon interference experiment that we are doing here. And by measuring now the widths of these, or the distance between these fringes, we can measure the wavelengths of these polaritons. In this case, we measure 230 nanometer. But what I should say is that the wavelengths that we use for illuminating the tip is 10 micrometer. So that is mid-infrared wavelengths. But for the photon, but the graphene plasma polariton is 40 times smaller, so it's an enormous compression. And that would be impossible to see with a far-field technique. So we can see that with a SNOM, thanks to its capability to focusing the incident field to these enormously sharp spots that carry enough momentum to launch these polariton waves. Now I have here a simulation how this actually works. So that is now, instead of graphene, we have here a numerical simulation where we have a point dipole source that excites these polaritons, and we scan it along here, and you see that these polaritons, they propagate along this lap here, and through this reflection at the edge here, we see these interference fringes. Okay. So now what we can do is we can take such images from these images here, right? We can extract line profiles. As I said already, from the line spacing, we get the wavelengths of these polaritons, and from that we can measure the dispersion of these polaritons. But we also will see that they decay over time, and from this decay, actually, we can learn something about the imaginary part or the damping of these polariton waves. There's a variety of things that we can do. So that's another schematic view. So we can image or we can scan perpendicular to the edge here at various different frequencies. What we will see is different spacings between here these peak positions, and from that we construct the dispersion relation of these polaritons. So what I also want to point out, what I showed so far was imaging at individual frequencies. If one has a nano FTIR spectrometer, then one can do so-called hyperspectral imaging, where we scan the tip perpendicular to the edge here, and then at each position we record a spectrum, and that gives then rise to these so-called hyperspectral line scans, where we have the frequency on the vertical axis and the distance here on the horizontal axis. And so if we perform such an image, we see these fringes here, and we see that if we go along a fixed frequency, we see these oscillations, and we see that the oscillation period becomes smaller at higher frequencies. So that shows us a dispersion. But now what we can do is simply a Fourier transform of this image along the horizontal direction gives us immediately the dispersion of these polaritons. And here we see these two polariton branches, which I don't have time now to go into detail. So I have to skip here a lot of things because I was much too slow. So okay, so that want to summarize briefly the last part. So in the first part of the talk, I showed you how we can measure dielectric properties by collecting light scattered at the AFM tip. But if we have materials like 2D materials that host these compressed surface waves, then we can perform so-called polariton nanoimaging or interferometry, from which we can learn about polariton properties, dispersion, damping, and so on. But what I have not had time to talk about is we can use the tip also in a more passive fashion, where we, for example, put polariton launchers on top of, in this case, graphene sheet, then like an antenna. Then the antenna could launch these waves, and the tip can scatter them out. And that's a very nice example that I find very, very impressive from last years. Here, an antenna was placed on molybdenum trioxide, and so-called hyperbolic polaritons were launched by this wave. Here one sees this in the simulation. These waves propagate away and then propagate through an interface and undergo negative refraction. So that's a planar interface. The waves diverge here, but on the other side are nicely focused here. And that was done by tracing here via the light scattering from the AFM tip, the wave fronts. And I think this is a really nice example for polariton mapping. I think with that I should stop, and thanks for your attention.
Thank you, Rainer, for this wonderful lecture, a wonderful overview on scattering SNOM. So much evolution over the last 20 years. I'm sure there are a number of questions for this lecture. Who would like to start? Everyone understood everything? Yeah, maybe I start with one. Oh, is there one here? Yeah, please. Is there a microphone? Well, I run with the microphone.
This might be a very naive question since I'm not familiar with the technique, but I mean, since these 2D materials are highly affected by charging or electrical fields, and obviously the tip is affected in polarization with the sample, how does this, can you comment on invasiveness of the technique in this regard?
Invasiveness of the technique?
Yeah, how much basically the measurement affects the material?
In principle, not much. I mean, the tip is not. I mean, if you may have some effects if you make some electrical contact between tip and sample, but in principle, the tip is grounded, and as if, let's say, it's rather neutral. So there may be some heating effects, but it hasn't been observed. There is. If you apply very high large powers, then eventually you can drive some thermal processes. People are using the technique sometimes for kind of modifying sample properties. I think what was done was changing a secondary structure of proteins. But if you look at crystals, metals, and so on, there is normally it's rather non-invasive. I mean, in terms of material property changes. What we measure here is not necessarily the intrinsic properties of the sample because of the near-field interaction. Yeah? There's an interaction, and that's why we need these models to extract the pure material properties. But I think you mean more like really changing the material itself, right? Yeah. Not that I know, only in specific cases. So in principle, it's a non-invasive method. I mean, if you prepare the sample as it is and it's in its natural state, you don't need to. You're not invasive. Of course, if you look at sample cross sections, because you have a complicated 3D material, you need to prepare it somehow. And in this case, it's invasive. But if you just exfoliate graphene and you image it, then nothing happens to the graphene. It would be unmodified.
Another question over there. Well, this is a tutorial, so don't hesitate asking every kind of question.
Okay, thank you very much for the nice introduction. I was wondering, what is actually the parameter that sets the length or the scale for the spatial resolution in those measurements? So suppose you have a homogeneous, in your models you mostly assumed homogeneous materials, I think.
Yes.
Okay. So suppose you have a metallic environment and then a dielectric patch in the center. how big does it have to be?
So I'm not sure whether I understood completely. So you're asking about what determines the spatial resolution, right?
Exactly, yes.
Okay, so the spatial resolution is basically given by the tip apex radius, right? So if you can roughly say, as a rule of thumb, if you have a 20 nanometer tip radius, you get 20 nanometer resolution. Then, of course, one can fine-tune that via the tapping amplitude and the demodulation order. For example, by going to higher demodulation orders, you can kind of achieve something what one calls a virtual tip sharpening, so you can increase the resolution a little bit, maybe a factor of 2 to 3, but not much more. So with the standard tips of 20 nanometer, 20, 30 nanometer, you achieve this resolution. But now, if you go to, let's say, just recently, 2 weeks ago or so, a group of Rupert Huber, they did a similar experiment, slightly different, and they achieved even down to atomic resolution. So that's possible. But with the s-SNOM, the way we're operating it here, it's just the tip radius. I mean, we try to shrink the tip radius below 10 nanometer, and we got signals. We achieved a resolution in some few cases of below 10 nanometer, but then the signal to noise also became rather weak. So yeah, essentially it's the tip radius with a fine-tuning of some of the operating parameters. That's more or less.
Okay, thanks.
Maybe time for one more question.
Yeah, thanks. I want to follow up on the first question here. Could you estimate the typical strength of the field at the tip relative to the strength of the incident infrared wave that's coming in? In other words, is it like a factor of 10 or a factor of 100?
Okay, so from numerical simulations, I can tell you. From measurements, I think this is it's tricky because of modulation, demodulation. I mean, this question I get since 20 years, and I try to avoid giving a precise answer. No, I mean, it depends. So these tips, we operate them from visible to terahertz, right? And we have different tip lengths. And then it depends whether you have a geometric resonance or not. So typically, we all don't have that. We typically have the lightning rod effect. And in the infrared, I would say 20 to 30. We just did recently some calculation, field enhancement. That would mean an intensity enhancement of, let's say, 100 or so. Now, if you have now the tip above silicon carbide, for example, and you drive that in resonance, then our calculations indicate that you have field enhancements of up to 1,000, which then would be 1,000 square, right? It's huge strengths. But I also have to say that if we image proteins, we never saw that they are denaturate. And we know that proteins denaturate rather quickly at whatever, 60, 70 degrees. And with the normal power, we never saw this. So in this regard, I really don't know. Calculations say, well, let's say 100 to 1,000. That's what I would say, roughly.